It's my very great pleasure to introduce Phil Blunsom. Phil is a postdoctoral research fellow at the University of Edinburgh, and his work is on applying machine learning to complex structured problems, in particular natural language processing problems like language modeling and machine translation and grammar induction. So Phil has had an amazing productive year last year. He had publications in ACL, EMNLP, and NIPS. His work is very, very good, and a lot of the students here have described his work as some of the most exciting research going on in machine translation at the moment. So with that build up, here's Phil.
No pressure.
Thank you, Chris. Very kind. Okay. So as Chris said, I'm from the University of Edinburgh, and the work I'll talk about today was done in combination with a few other people there, Miles, Trevor, and Chris Dyer, who some of you may know. Okay, so just a high-level outline of what I'll talk about today, very generic. I'll start with some introduction and talk about the sort of models that I'm interested in working with, and then I'll describe the models, the particular generative models that I'll use to model machine translation in particular. And then I'll talk about two ways of performing inference in these models. The first being variational inference, and then I'll talk about an alternative to variational inference, and I'll motivate why we might like an alternative, and that'll be to use a sampler. And I'll finish with some summarizing comments. Okay, so I'm sure most of you are very familiar with the general aims of machine translation, but a high-level introduction. We just want to take text that we may not understand, in this case some Chinese text, and render it in a form which is usable by for a particular user group. And so ultimately this is AI hard. We need world knowledge. We need to reason about things which are not in the text. But that doesn't stop us trying. Even though we can't manage to model those things. And so in statistical machine translation, we really concentrate on trying to learn translation models from what I'd call naturally occurring data. So not data that's been annotated particularly for the purpose that just happens to be around, like parliamentary proceedings or things that are parallel corpora. So it works. We can translate text and get really quite good translation. So in this case, Arabic, news stories. And this is very encouraging. And so we might think, well, what more is there to do? But if we try a different language, such as Chinese, we get a very different result. And so both those two examples are just state-of-the-art phrase-based translation models trained on very similar amounts of text, about 10 million words, and very similar models in all respect, and you get radically different results. And the problem here is that it is mostly a problem of word order. So the Arabic has a very similar word order to the English target language, whereas the Chinese does not. And the problem is that we really, in our translation models, don't have any sense of structure. So if the structure between the input and the output is very similar, then we can do well. But if the structure is different and we have to create that structure ourselves, we do very badly. And so in this talk, I'll talk a lot about structure and whether we can induce better structures. So current MT systems I would describe as a little bit of a mess. There's a lot of heuristics involved that have built up over time, largely by people trying things. If they work, we include them. If they don't work, we don't include them. And so we get this long pipeline of disparate processes we perform. And some of them are based on probabilistic models, such as the word alignments, and others are just heuristics that people came up with and other people have used since then. So in my mind, this doesn't give us a well-defined model of translation. And it's also very hard to work with. If we change any part of this pipeline, the results are very hard to predict. For instance, we can make the alignments much better, and we can show that they're much better, but they make no difference to the translation or make it worse. So there's a lot of effects going on here which are hard to work with. So in my work at Edinburgh, I'd really like to simplify this and think of things in terms of probabilistic models that we can reason about and that we can analyse, and therefore have a more predictable outcomes with our experiments. And so in some earlier work I did, I worked on treating the learning of the parameters in the translation model as a machine learning structured prediction problem. And so using models with millions of features and how we can learn these from parallel data. And in doing that work, it quickly becomes apparent that the underlying translation grammars or phrase tables that we work with are really quite rubbish. There's a lot of noise, there's very little structure that informs the language. And so then I became interested in working on the first problem, and that is treating translation model induction as essentially a grammar induction problem. And so that's what I'll talk about today. Treating this problem as a non-parametric Bayesian model induction problem. Okay, so I'll just give a brief introduction of synchronous grammar. I'm sure many of you are familiar with this, but it's just so we know we're talking about the same thing, and a particular subclass of synchronous grammar that I'll work with, sometimes called ITG, inversion transduction grammar. And I'll just run through a derivation and highlight rules as I use them on the top and as they get generated on the bottom. So the first thing we do in generating a pair of parallel strings is to have a goal symbol, and the goal symbol rewrites as a left and right symbol. We can then replicate that symbol, and the boxes indexes denote the ordering between the relative ordering between the symbols on the source and the target. We can introduce a lexical translation, and we can keep following this process, replicating variables, introducing more lexical translations. In this step here, we actually use a different rule to replicate the variables where we switch the order, the relative orders between the source and target, and that allows us to do reordering, which is crucial for translation. And in this case, as we introduce more lexical content, it allows us to represent the verb movement in German. So where the verb moves over the noun phrase. Okay, so this is the basic grammar, sorts of grammars that I'll be trying to induce here. And I'm not arguing that these grammars are sufficient for modelling translation or that they're in any way good for modelling translation. They're more good for doing experiments and trying to learn about inducing grammars. So I'll talk a bit more about where we might go beyond these grammars a bit later on. Okay, so current approaches to inducing synchronous grammars for translation are based around heuristics, and generally heuristics which have come out of the phrase-based translation work where things have been successful. They've been ported to the synchronous grammar cases. They're not very satisfying. They produce massive grammars, hundreds of millions of rules, very noisy. They're purely lexicalized in the case of Hiero, or rely on supervised parsers or some such to get annotations. And so today I'll talk about ways of doing this in a probabilistic model, and also without relying on any external annotated resources like tree banks or anything like that, trying to induce a structure simply from the parallel corpus. And the sorts of things we might hope to be able to induce in this case is something like this, some sort of labelled derivation tree for a translation pair here, a Chinese to English pair, where the numbers denote some sort of constituent categories, and we learn the translation units at the leaves and the relative ordering. So this is the basic aim. Okay, so now I'll talk about the actual generative model that I'll use to model these processes.
Excuse me, you said a pair has heuristics.
Yep.
Can you tell us a little bit about that?
So it uses a very similar approach to the way phrase-based models are induced. So you start with word alignments, but you create multiple word alignments. You combine them with a heuristic combination, and then you have David's rule extraction is an adaptation of Philip Cohn's phrase extraction, where you look at so-called consistent phrases on word alignments by drawing boxes around them. And then given those, you count how often you see them and you use those as features. So there's no actual probabilistic model there. That's just things that people tried and they worked. And they work quite well, but in my case, I'm interested in having stronger explanations of what's going on.
Phil, can you say for people who aren't familiar with this, how probabilities are assigned to the rules extracted by that heuristic procedure in HERO?
So you count how many times you extract a rule. So for every alignment, you look at the phrases you could extract, and you count once for each one. And if you actually think about this, it doesn't really correspond to any generative model, because you extract a long phrase, you count it once. You extract many smaller phrases within that long phrase, and you count each of them once. Whereas really, if you thought about a generative process, a small phrase would be used many more times than a long one. But there's some very complex interactions that happen in that process, and they actually turn out to be quite good in the way that it's done. But that's another story. So the generative process for these derivations, and I'll run through them at the top and at the bottom. I'll give the actual distributions for the variables as they're being drawn. And just a word on notation that I'll use quite a bit. So this means that Z1, where Z is the label on the constituent, is drawn from a multinomial parameterized by phi s. And so, the first thing we do in starting our derivation is draw a start symbol. And here we draw the start symbol 1 from a multinomial. Next, what we do is draw a rule type. So in my model, we have 3 types of rules. We have monotone production, so that's where a variable produces 2 child variables in the same order. Reordered productions, where that order is reversed, and terminal emissions, which emit a phrase pair. And here I've used a box to denote a monotone production. So this is producing 2 child variables in the same order on the source and target. So that's the TI is a type, and that's drawn from a multinomial, and the parameters of the multinomial are phi, Zi, and the T just means the type parameters. So it's drawing from a multinomial parameterized by phi.
The time is...
Sorry?
You said time?
T is a literal symbol there, is that right? It's identifying which phi it is. It's phi superscript T.
It's phi. It's the parameters.
T is not a variable. It's part of it's phi superscript T is one symbol.
You said it's a variable. It's a random.
TI, the lowercase ti is a variable. That's the type. Uppercase T on the superscript just identifies the parameters. Sorry. A little bit ambiguous.
One more question. You were speaking about 3 kinds of rules. Does that mean that by the time you do that, you already have them listed somewhere?
We know it, so it's in the model definition what our 3 kinds of rules are.
Yeah, but a listing of them is there too?
Yes.
So we already have the rules, we just don't know
Only the types of rules. We don't have the entire grammar in that. These rules may be instantiated with many different categories. So the types of the rules come simply from the fact that we're using a binary branching synchronous grammar. So there's no other types that could be used in such a grammar. If you had a different grammar, tree substitution grammar, you would have different types. It comes from our choice of grammar.
But I think Fred's question is, you are going to learn what phrases actually are instantiations of those 3 different types.
Oh yes. Okay, so we've chosen a monotone rule. And the next thing we do is generate 2 child labels. So we've chosen it as monotone, and we generate 2 child constituents. And again from a multinomial, and this time we're generating Z left and Z right, ZL and ZR there, again from a multinomial, a different set of 5 parameters. And we basically repeat this process. For the next variable, we again generate a type. Here I use a circle to denote a terminal emission we've chosen. And given it's a terminal emission, we then generate the actual phrases. In this case, we have a Chinese question mark going to an English question mark. And we keep going through this process. We have a diamond for a reordering rule we draw. We draw its children, and then for each one, we continue And so the result is that we generate the entire translation in this fashion in an appropriately ordered sequence. So this is the underlying generative model. And this is, so we could say, well, why don't we just train that for maximum likelihood given our data, which a number of people have suggested doing or done. But it's a bad idea.
Just clarifying before you go on, a box that is sort of standing on its base is a non-inversion rule, and a box that's standing on a corner is an inversion?
Yes, a diamond is an inversion.
So in Dekai's term, there will be a little bar under that.
Yes. Yeah.
So, so far all you've done is, this is what an SCFG is.
Yes.
Right.
So if we just train this for maximum likelihood, the problem is that there is we know what the solution is if it's a maximum likelihood, and that's that we just learned that every sentence should translate, in the training data should translate as its target. So that's what's often referred to as a degenerate solution, because it's uninformative and it doesn't generalize. So we're going to need to encode some sort of smoothing or prior information in order to get anything interesting out of a model like this. And that's largely what this work is about, coming up with interesting ways of encoding that. So what I'm going to do is extend work in monolingual parsing, in particular Percy Liang's work, which he referred to as a hierarchical Dirichlet PCFG. I'm going to extend this to synchronous grammars, which basically means going from 1 dimension to 2 dimensions. So we're going to use that to induce the grammar, and particularly one of the main things of note here is the use of a hierarchical strict breaking prior over constituents. And so I'll talk a little bit about what a stick breaking prior is. It may not be familiar to many of you. And the aim, what we want to do is we have some sort of inventory of categories that we might label our grammar with, and we need a distribution over these. And we want to allow, we don't know how many of these categories there are. We don't want to fix it a priori. So we need a distribution over an infinite space of categories. And we get that with an analogy to a stick. So we have a stick of unit length, and we're going to break bits off the stick proportional to how much is left. And we do this in a mathematical sense by drawing pi dash from a beta distribution, and then that denotes how much of the remaining stick we break off. And so that product there is just breaking off pi dash proportion of what's left of the stick. And the effect that this has is that the expected length of the breaks of stick will decrease over time. They won't absolutely decrease, so sometimes we'll break off something longer than the previous one, but the expected length will decrease. So what we'll get is a distribution weighted towards a small number of categories, but over an infinite number. And we can parameterize how weighted it is with an alpha parameter. So that's the distribution we'll use for the constituents. And the second construction that we'll need is a Dirichlet process. We need a distribution over pairs of child constituents. So we're now in our grammar for a parent constituent, we generate two child constituents. So we need a distribution over pairs rather than single constituents.
That's right. And to be clear, the last line on the slide is X, the left-hand side non-terminal. And you're generating a pair of right-hand side non-terminals for that?
Yeah, conditioned on a parent. Yep.
Yep. And X is the parent. Or you've left the parent out of the notation.
No, yes, X is the parent. Yep. Sorry. So we do that by, so pi is our stick, it's our distribution over lengths, and so we do that just by taking a Dirichlet process and taking the square of pi as its base parameter. So now we have, so that square of pi just, you can imagine as being a two-dimensional grid over sized units rather than a one-dimensional stick over breaks. So that gives us a distribution over pairs. Okay. So now for the somewhat scary full model description, and I wouldn't expect you to follow this particularly closely, but the main thing I want to show here is the way that the prior distributions link together. Because the crucial thing we need to do in a model like this is make sure that the actual the distributions for the different rules are all referring to the same constituents. So the process is just as I showed earlier. The first thing we do is draw a start symbol, and that's highlighted on the top there. Its prior distribution is highlighted on the right, being for phi s is distributed according to a Dirichlet process. In this case, just a one-dimensional one because we're only drawing one symbol. And those pi themselves are in turn distributed according to a stick breaking process. So this is the hierarchical nature. The next step is that we draw a type. This is a much simpler process. We only have 3 types, which are a finite number. So we draw that from a finite Dirichlet, and there's no hierarchical prior going on there. So given we've drawn one of these types, monotone, reordering, or emission, in this case a monotone, it has a prior, which is a Dirichlet process. It's using this squared base parameter that I referred to over pairs of children. But the key thing of note is that it's using the same top-level stick-breaking prior distribution as the start symbols were drawn from. So in this way, we're tying together our symbol inventory so that they're all our distributions are referring to the same set of symbols, which is crucial for the model to work. The same is true for the reordering rules. In this case, we see that it's a different Dirichlet process that we draw the reordering rule parameters from, but it's the same top-level process. And finally, for the emissions, they are also drawn from a Dirichlet process, so we notionally think of an infinite space of possible phrase translation pairs. So any string we can generate going to any other string we can generate. And then we have some base parameter, which I call P0 here, which is just a way for us to encode prior knowledge about what are good translation pairs. So that's where we can introduce some prior knowledge. So that's the full model specification. So a few words about this P0 distribution. So in the experiments I'll show, we experiment with 3 different distributions. The obvious one is just a uniform distribution over all possible phrase pairs. The second one is to use a word-based alignment model, in this case IBM Model 1, as a prior distribution. So those of you not familiar with IBM Model 1, it's essentially a co-occurrence style generative translation model, which is order-free in the translation units. Doesn't model word order, but it makes a good back-off. So the way to think of these different hierarchical priors is essentially as back-off, much like in language modeling or similar things. We're basically backing off to simpler and less sparse representations in the modeling. So in this case, we're talking about backing off from modeling phrase pairs, which are going to be quite sparse if you imagine long phrases map into each other, and we're backing off to IBM Model 1 in this process through the prior. And the last one is relative frequency, which is just the standard way of estimating phrase probabilities that's currently used in machine translation. And we get that simply by looking at an aligned corpus and counting the frequency of the various rules and using that as the P0 prior. So you can think of this as a way of taking what is a biased inconsistent estimator, the relative frequency, and incorporating it into a more principled probabilistic model. Okay, so now to inference. So the model I've described is rather complicated, and inference in this model is particularly complicated, particularly because the way the priors interact is that all our training sentences become dependent on each other. So any decision we make in one sentence or one part of a sentence is dependent on every other decision we make in the corpus. So we can't use dynamic programming to exactly do inference in this model because of these dependencies. So instead we can use an approximation which allows us to use dynamic programming. And this is the variational mean field approach. And so I'm not going to go into too much detail with how this works. There's quite a lot of maths involved, but I'll try and just give the high-level intuition. And that is that we have some distribution P that we can't do inference within, or for. And so we come up with a distribution Q and assume some sort of factorization which makes it possible for us to do inference. And then we minimize the divergence between Q and P. So in this case, Q, we assume that our parameters theta and so Z is, you can think of as the expectation over trees for our parallel sentences. We assume that these can factorize independently. And so by doing inference within that model and minimizing the divergence from P, we can show that we get a bounded approximation of the true posterior. And this is a increasingly common approach in Bayesian inference. And so what this actually looks like in practice in this case, we have a very complicated equation, but it's actually very close to what many people are familiar with in the EM algorithm. So in the EM algorithm, we estimate expectations in parsing, we estimate expectation over trees using the inside-outside algorithm. And then we re-estimate our probability weights using a ratio of expectations. Now, if you have an EM algorithm implemented, turning it into a variational algorithm is incredibly simple. So highlighted here, you can see those core counts, which are the expectations. That's exactly the update you do when you're doing EM. So all we've done is wrapped these updates in a digamma function, which is a result of the Dirichlet priors that we use. If you integrate them, you end up with a digamma. We have an additive number on the end there, which is you can think of as similar to additive smoothing, and that comes from our prior stick breaking prior, and then we exponentiate the whole thing. So this in practice, this is extremely similar to having an EM algorithm. We iterate from estimating expectations on our parallel corpus to re-estimating these weights W. There's only one small difference, and that's we have an extra step where we re-estimate this stick pi. And there's an optimization equation we need to do that, but I won't go into that. That being said, if you have an EM algorithm, it's very simple to turn it into a variational algorithm.
Excuse me, the denominator is a sum over all CM.
Yes, so sorry, the star notation there means, so the top count is over a particular rule, and the bottom count is over all possible rules of that parent constituent, Z of Z. Yeah.
Well, it's only reversing rules, right? Only diamond rules.
Yes, sorry, I didn't say that. This is just the update equation for a reordering rule. We have a similar one for monotone rules, and they're all basically the same structure for the monotone for each of the distributions. Okay, so the first experiment that I'll talk about is a synthetic experiment, which are not very common in machine translation, but I think they're quite handy for understanding how our models work. And so I've got a synthetic grammar, very simple grammar. It's just one level. We have a non-terminal S, which can generate pre-terminals A, B, or C, and each of those can generate terminals A, B, C, D, etc. So we have A's and C's, which generate in a monotone order. B's generate reordered, and there's some ambiguity in the terminals. And so for the experiment, what I do is generate 10,000 training examples from this grammar, just with uniform weights. Then I train the Bayesian model I've described and a maximum likelihood model, and compare the distributions I estimate to the one I generated from. And these graphs depict those distributions. So the blue is the Bayesian model, the red is the maximum likelihood model. The graphs are the posterior over categories on the left for the non-terminals, the internal non-terminals, so in this case the S symbol, and the right is the one over the pre-terminals. So if we look at the left graph, it's on the y-axis is the posterior probability. So we see that the Bayesian model has just allocated all its probability to a single category, which is exactly the sensible behavior, because we know that there's only one category S. Whereas the maximum likelihood model has split up the probability over two categories. And it's done this basically because it can. There's no prior that pushes the model to find a small number of categories, and so this is a perfectly sensible local optima. For the maximum likelihood models, there's many other solutions that it could come up with, including the correct one. Whereas the Bayesian model has a strong bias towards finding the minimum number of constituents to model the data. We see the same effect when we look at the emission distributions. Again, the Bayesian model has found three categories for the emissions, which correspond to the A, B, and C, whereas the maximum likelihood model has got somewhat confused. It's combined two categories into one in the category 1 there, and it's split up the third category over two other categories. And again, this represents a poor local optima.
Are these results, it's always nice to look at the toy examples, I like that you do this. Are the results sensitive at all to your choice of alphas?
Not particularly, but mostly because it's a very small experiment. So any bias on the Bayesian model is going to push it towards one category. If we were talking about hundreds of categories, then yes, you'd see some sensitivity. But because whereas the maximum likelihood model is extremely sensitive to initialization.
But excuse me, you're doing EM, and EM actually can get trapped into local maxima, right?
It's strictly speaking, it's EM for the maximum likelihood model, and it's the variational inference for the Bayesian model.
Right.
Both are subject to local maxima,
Right.
but the Bayesian model has, I would say, I wouldn't state that it's convex, but it's much more convex than.
Much more complex.
There's less local optimum because it has that prior pushing it towards a single category. It's essentially a smoothing effect. Okay, so for a real translation experiment, I'll experiment with the IWSLT data set. And this is a smallish data set, about 40,000 sentences, mostly quite short, and from a travel domain, lots of questions and things like that. Where is the bus stop, etc. And I'll use the 2005 test set, and the blue metric that, if you're not familiar with, is just an n-gram overlap counting metric. And in this case, we have quite a lot of references for the test set. So now we get to the one caveat with this variational approach is that we cannot do dynamic programs over infinite spaces. So we need to restrict the space that we're doing inference over in some way, and this is referred to as truncation. So in this case, we need to restrict the number of categories that we perform inference over, and we need to constrict the space of possible phrase pairs that we perform inference over. So in this case, I'll just present experiments with a small number of categories, 1 to 5, and the phrase pairs are restricted to the same set that a phrase-based system would extract. Now, these are not desirable restrictions, and I'll come back to this later on in ways we can get away from this. But it serves the purpose of exploring the model initially. Oh, and there's so because we restrict ourselves to what a phrase-based system might use, it means that we can't actually model all of the parallel corpus, because sometimes we can't produce a given target sentence for a given source sentence with the phrases available. So we need to discard those sentences. So that leaves us with about 33,000 training sentences.
And that is the result of pruning the set of phrases,
Yep.
Rather than pruning the number of constituent symbols. Even with an infinite number of constituent symbols, you might still have inside-out permutations that you couldn't model if you only had single word paraphrases, right?
Yeah. So the constituents won't affect the reachability, only the phrases. So here's the results. This is just using a single category, so we have no hierarchical stick breaking prior in this model. This is just doing inference over the phrases. The black on the left there is the maximum likelihood model. The grey is the Bayesian model with a uniform prior, and the other two are the more informed priors. And we see essentially what we were hoping to see, that the maximum likelihood model overfits, the Bayesian model does better, and as we incorporate more informed priors, things get better again. So this is good. If we go to more categories, so now we have multiple constituents in the model, we actually see that the maximum likelihood model gets worse. It's essentially overfits. It doesn't really know what to do with these extra categories. Whereas the Bayesian model does get slightly better. But the effect is very small in this case. So the first question with that model to ask is, well, what constituents does it actually come up with? And of course, we wouldn't claim to be seeing things like noun phrases or verb phrases emerging from 5 categories. But what the model does find is, as soon as you give the model more than one category, it will allocate a start category, a goal category, which is quite a sensible thing to do. That's the S symbol. And after that, the interesting thing is that it allocates a start of sentence category. And I put that mostly down to the number of questions which are in the data. So there's lots of what's, where's, when, and it learns that these start sentences. And they're also generally reordered in between the Chinese and the English. As in the example I presented earlier, the where moves over. And after that comes end categories. But that's essentially the limit of what we discover with small numbers of categories.
Quick question, is the end category because of some sort of sentence and punctuation?
Yeah,
Because
it's mostly likely to be the full stop and things like that, question mark. And that's a less strong effect than the start of sentence. Obviously, this 5 categories is far too few to learn anything particularly interesting, and we need to increase that. And the reason I haven't is because scaling is rather difficult with this model. So with a single category, it's actually quite efficient. We can do inference over quite large data sets. As soon as we start adding more categories, we have cubic scaling. So because our rules are parent goes to 2 children. So things get slow very, very quickly. In the case of 5 constituents, we're 125 times slower than a single constituent. So this is undesirable. If you don't do any pruning, yeah.
So, so in the variation method, how do you do a prediction during the test time?
So we use with the variational inference, we're re-estimating these W weights, and you can do inference with those weights themselves, and you can show that it's very ambiguous what you should do with a variationally trained model at decoding time, and there's particular different strategies. If you use these variational weights, you can show that it gives a bounded error on what the true decoding posterior would be. So
That means you do not integrate all the possible parameter values, right?
well, so the way to think of these W weights is not as the actual parameters. They're we refer to them as subnormalized weights, and they incorporate an uncertainty from the estimating out, and so that's why you can get a bound from using them. So they're not directly equivalent to model parameters, but they are just another set of parameters which you can decode with, which allow you to bound things. And so if you look in the relevant paper for this, I have that bound there. Okay, so I've talked about variational inference, and you're probably starting to think that there's some problems with that approach, limitations we face from truncation and the complexity. So this led me to try a different sort of inference, and that is to use a sampler. And this basically covers the 2 popular approaches within Bayesian inference. You'll generally see a lot of papers with either variational or sampling. So I'll print. Okay. So the problem we faced with variational inference was one, the need to do this polynomial time dynamic program, and that was only really tractable because we truncated the phrases. If we didn't do that, we were looking at an n to the 6 dynamic program, which is not terribly efficient. So instead what we're going to do is integrate out the parameters in our Bayesian model, and this gives us what's often referred to as a collapsed Gibbs sampler. And then we can do inference simply by representing a set of sampled derivations for our corpus, and so we never have to store more than our current sampled set of derivations. And this allows us to actually do, provably in the limit, exact inference without any truncations, so over the entire space of translation units. And it also actually allows us to scale things quite a lot better, because we can do this sampling quite quickly. In the experiments I'll show here, all the experiments are just with a single category. I haven't yet experimented with multiple constituent sampling models, and I'll mention how we go about that at the end. So some more nasty math. When we come to start trying to sample these distributions, we need, again, we need a distribution over phrase translation pairs, but we need one that's very fast to calculate, otherwise our sampler is going to be incredibly slow, and model 1's quite slow. And we can't use the relative frequency because that relies on us having a fixed set of phrases that we can estimate the probabilities for, but because we don't know what the phrases are, we can't a priori estimate their scores. So what I'll do is define quite a simple prior, and And what this says at the top is that the probability of a phrase pair ENF factorizes independently across the source and the target. So we say that the prior treats the source and target independently. And so then we make this into a hierarchical Dirichlet distribution again by introducing a Dirichlet process parameterized by the final back-off level in our model, which is a prior over strings. So this bottom line is just a distribution over monolingual strings. And people often use geometric distributions for this sort of prior. Here I've used a Poisson just to really encourage the model to find very short translation units. And the effect that this has, the effect that this factorization has, is essentially what we're saying is that our phrase translation pairs should include frequent monolingual strings. And this is similar to a sort of constituency argument that frequent strings are more likely to be in some way related to the structure of the languages. So when we come to define a Gibbs sampler, what we need to do is define operators for permuting these derivations. So we have a derivation, a current parse tree, and we want to make small updates to it to explore the space of possible trees. So when I started on this work, I realized that I don't think anyone's actually come up with a sampler for a Gibbs sampler for trees before, even though it could actually be a very useful thing in a number of different applications. And so this is the sampling operators that I came up with. And there's many different variations you could come up with, but these are just the two ones that occurred to me first. And so what this first one is what I refer to as a split merge operator. And this operates on the terminals of the derivation, terminal phrase pairs. So either a single phrase pair here, the boxes denote words, or a pair of terminals sharing the same parent. And for any one of these cases, we sample from all of these cases a new configuration according to our probabilistic model. And these cases here denote empty strings. So we may want one unit to translate to an empty string. So each time, our sampler basically traverses through the derivation, and when it encounters terminals like this, it will sample from these possible options of splits. And you can see that this sampler will be quadratic in the source and target lengths of the two phrases. So as long as our phrases are reasonably short, which we expect in translation, our performance will be quite good. Our real-time performance will be quite fast. So that operator operates on the leaves of the derivation. The second operator I need is one to operate on the internal structure of the derivation. So that's the non-terminal node. And so I have what I call a reparent operator, which adds and removes internal nodes. And so if you look closely at this diagram, you'll notice that if we remove a node and promote its children, we'll actually end up with a ternary rather than binary node. And so I just make the adaptation to the grammar that I allow ternary nodes. And this is mostly for convenience of the sampler. If you don't do this, it's actually far harder to come up with a sampler for binary branching grammars. If you did this in dynamic programming, it would make things a lot heavier. But for our sampler, it actually makes things more efficient. So this sampler simply adds or removes internal nodes. So I'll run.
You don't allow nodes with more than 3 children?
No, 3 is my limit.
I see. Okay, so there are some moves that you can't remove remove a node that already has 3 children.
Yes. Yep. And I also don't allow a unary node, so you cannot insert a node in a binary one. So it makes things restrictive, which makes things fast.
Okay. And if we think about this, we'll see why the chain is connected.
What's that, sorry?
We'll see, if we think about this, we'll see why you can get from any tree to any other tree by...
Yes, very true, sorry. So applying these two operators, we can show that we can go from any one tree to any other tree. And you can do that by making lots of small changes, but the easiest proof is that you can just collapse everything into one big phrase pair and then resplit it again, which is obviously not a very plausible explanation, but is a sort of base proof that you can reach any tree from any other tree. So I'll just run through a quick animation of how these operators permute the tree. So here I highlight part of the tree that an operator might choose, in this case a pair of terminals. And then we sample from the possible segmentations for these. And in this case, we might sample to join them together. So now we have a single terminal there, translating as the noun phrase. Next operator might be the reparent one, and we might choose an internal node in the tree. And we might sample that we should remove that node and replace it with a ternary node. Again, we may select a different part of the tree to terminals, and again look at their segmentation. Sorry, in that case that was the reparent sampler. So in this case we looked at whether we should introduce a node, and we sample to introduce that node below the parent. So you can think of this as we've sort of rolled the node from one side to the other through these steps. And again we choose some terminals, and then we might sample that we should move the determiner over onto the noun phrase and come up with a slightly more appealing segmentation of the translation. So that process is, the sampler just goes through this process over and over again, permuting the tree, and this defines, and this can be seen as drawing samples from the distribution defined by our model. And so what I will refer to as a single sample is visiting all the nodes in a derivation with each of these samples, with each of these operators.
Do I understand that the number of terminal symbols, terminal states, is going to be equal to the number of words in the source language, and you start with an arbitrary tree which implements that, and then you start screwing around?
I'm not sure I quite follow you. And do you mean the number of segmentations that we can choose?
No. Well,
There might be
you
multiple
did not
resolutions.
change, during the examples you were giving, you did not change the number of bottom circles.
He did actually.
I did
Yeah,
in the first one.
He started with 5.
So in the first one, in the first step, we can collapse.
All right.
So we can collapse and join. Yeah, and so yeah.
And the meaning of that would be that circle actually produces 2 source words, and in this particular case 3 target words. If you go back up a couple slides.
That one?
Stop here. So the first circle produced a pair of words, 1 Chinese, 1 English. The second circle produced 3 words, 1 on the Chinese, 2 on the English side.
Yep.
And an alternative would have been a single circle which produced the 2 Chinese words and the 3
Yep.
English words, which is what he used.
So a bigger phrasal translation unit. Yep.
And what is the starting configuration?
Okay, so we do need to initialize this in some way, and I'll talk about that in a slide or two. But the crucial thing to realize is, as I mentioned, the complexity is in the length of the source and target strings that we're sampling. So we could choose to initialize it with no segmentation at all, just entire sentence goes to entire sentence. Unfortunately, that would be incredibly slow. So yes, we do need to choose a initialization, but something to take into account when you choose the initialization is to make the phrases small so things run quickly. Yep.
So one thing you haven't focused on, which I'm not sure whether I see it all the way through, is how the alignment changes as a result of these operations. And you'd like to be able to,
So
you're sampling not just a tree, but a tree that produces an alignment.
So we can. So a derivation implies an alignment.
Exactly.
And the way I'll use this model is to sample a distribution over alignments, essentially.
Oh, actually, I'm sorry. You had this about 5 or 6 slides ago, where you showed what you did at the leaves and different ways of splitting, including swap. Yeah. Okay.
But the sense of alignment is a bit different because any phrasal unit we essentially view as fully aligned to each other.
No, this is fine.
I wasn't paying that much attention, but did the English sentence change during
No.
this process?
No.
Training.
So because it's a generative joint model, we only need to do inference over the observed strings.
And what will change is the alignment of the English to the Chinese.
Yep. So the alignment changes and the structure changes, and that's what we're exploring. So initialization. So the way I initialize this is just to use a standard alignment model as a starting point, but obviously we need a derivation structure which conforms to our grammar, and alignments won't necessarily do that. So we factorize that alignment, and I use a particular algorithm described by Hao Zhang to do that. still many sentences don't factorize into binary or ternary, many alignments don't factorize into binary or ternary structures. So in that case, I just start dropping alignment points until they do. So that's the initialization. So the way I use this sampler is we initially have what I call a burn-in, and that's where we just run the sampler for a long time, essentially trying to forget the initialization. And so we burn it in for 1,000 samples. So I run 1,000 samples through all the corpus. Then after that, for the next 500 samples, I take every 50th sample and I create a distribution over derivations from that. And that distribution defines a distribution over alignments, which define a distribution over phrasal translations. So this model doesn't directly give us an alignment, but it gives us a distribution over them from which we can extract our translation model. So first experiment, again with the IWSLT data. And the way I actually do the decoding is just to use the sampler to basically sample a phrase table. So to sample the phrases given these set of samples and their probabilities, again, given the expectations from the sampler. So this is the same IWSLT corpus. In this case, we don't have any problems with reachability because we can represent any possible. We can derive all our strings in our training corpus because we allow any of the phrase translations. And we see a nice improvement using the Bayesian inference on this IWSLT corpus. And so that's heartening. Sorry, the training data? Yeah. So this is the same as the earlier experiments, the IWSLT corpus, which was that travel domain corpus of reasonably short sentences, 40,000 sentences.
So this
one, yes.
Sorry, I don't understand the bullet point at the lower right.
The sampler is just, it can be used to sample a distribution over phrases, which I can then just feed into a standard phrase-based decoder. So
oh, I see. Okay, so you're just pulling those off the leaves, and you're throwing away the structure.
Yeah, and then I'm just taking lots of samples to calculate an expectation over the.
Yes. Okay. So I guess I'm troubled by this because I had been hoping to see a distribution over grammars.
Because there's no constituent labels, it doesn't really matter whether you talk about distribution over grammars or not. Well, you could directly translate with the ITG model, but it's a particularly poor translation model, so that wouldn't be a very good idea. As soon as we start adding constituents, then it's much more interesting to talk about directly doing the decoding in the synchronous code model.
Have you done that yet with the sampler version?
No, not constituents. Sorry, the other thing I should note is all these experiments I've also done with a Hiro-style SCFG system and see similar results, and they're in a paper. Okay, so that was the first set of experiments. But I think...
So here, you give something to sample some derivation during the training time, right? So can you just, during this time, can you just integrate all the parameters and to give something instead of...
Yes, you could use a sampler to do decoding as well.
Yeah, and did you do that?
No. You need a different sampler, which I haven't implemented yet, because now for these ones you're constrained in 2 dimensions, whereas decoding you're only constrained in 1 dimension. You've got a source sentence and you need to sample over all possible, so you actually need different operators. And so that's just a question of it's not yet implemented for decoding. But as soon as you start talking about trying to induce more constituents, then it's much more interesting to talk about doing the decoding with sampling as well.
Is the only extra constituent the emission part in the decoding?
Is the only what, sorry?
The sampler, the extra sampler that you need, the extra sampling operation you need is on the output side.
The only extra one you would need would be to change the output.
Right.
But because of the different nature of the problem, you would be able to do some more interesting things. When you do the sampling for the parallel sentences, you're quite constrained by that space. As soon as you take away one of those constraints, it would allow you to define operators which would make things work a lot more efficiently.
Okay, so as a easy first step, I suppose you could produce some sort of invest list using your Moses setup, and then use each of those as your space.
Yes, that's true. But as I mentioned to Jason, the ITG model itself I would not claim as a good decoding model because of the way it parameterizes reordering. So you won't get terribly good results doing that.
And also, is there any way to compare the result between the wave rational variation and the Gibbs sampling?
In this case, no, because you have the difference is one has a language model and the other doesn't. So that's why the numbers here are much higher because of the presence of the language model. It would be possible to implement that and look at it, but the problem is that we're now essentially solving a slightly different problem because with the sampler we can go beyond the constraints of the existing phrase set. So we've done this on the small corpus, but we really like to go a lot bigger because we know that translation models really need to be big to be effective. And so we want to be able to distribute this in some way. It's very easy to distribute the variational algorithm. It's just like distributing the inside-outside algorithm for parsing. The problem with the sampler is that every sampling decision we make is dependent on the state of all the rest of the corpus. So we cannot just distribute the sentences because all the processes would depend on each other. But there's been a number of works which have shown ways of approximating this quite effectively, in particular the one I cite here from Newman. And the idea is that we can ignore some of the constraints and still get very close fitting of the actual posterior. And so the way we do this is have n processes, each which maintain the full set of samples over the corpus, but only resample subsets of the corpus, their own subsets. And once they've finished sampling their own subsets, they then communicate what they've done to every other processor. And in that way, every sampling decision is being made with slightly out-of-date information, but not very out-of-date information. And that turns out to be a pretty good approximation and allows us to start distributing the inference. But this is approximate, I emphasize. So now we'll try some bigger data. In this case, some data drawn from the NIST evaluations, both English Chinese and English Arabic, both on around 10 million words. I use the same configuration of 1,000 sample burn-in, and all these are done on a single 8-core machine distributed across 8 processors. So I haven't actually pushed this very far in the distributed, so we can go quite a lot bigger. Okay. So the first thing to look at is how this distributed approximation performs. So the solid line there is a single CPU sampling on the, this is the Arabic corpus, and the dotted line is one distributed across eight CPUs. And they're both sampled for about 250 samples, which took quite a long time on the single CPU. And we can see that the two posteriors follow each other very closely. Sorry, each of these experiments was run 5 times or 10 times to get the error bars there. And so I'm reasonably confident that this is quite a good approximation of the posterior. So then we can do some experiments on this corpus. And so the evaluation here is on 3 test sets from NIST, MTO 3, 4, and 5. The black bar is the standard phrase-based system. The blue bar is the Bayesian model, and the grey bar is actually just evaluating the initialization alignment. So this is the alignment I used to initialize the sampler. So in each of the cases, the sampling model outperforms the baseline. This is good. The changes are relatively small, So it seems to be working for Chinese. We're getting quite good. If you look at the actual sample alignments, they're quite good. The one strange thing is that we actually see the initialization outperforms both models in one case, and this is interesting. But if we look at the Arabic, it's more interesting because the initialization does really well. And the Bayesian model actually underperforms the heuristic in 2 of the 3 cases, and then it's about equal on the other one. So what's going on here? And so my analysis of this is that Arabic has a very strongly correlated word order to English, and our current existing translation models are basically predicated on on this sort of relationship. So they have a strong monotone bias built into them, particularly the alignment models, but also the heuristics used to extract phrases.
So the heuristic system has the language model and tuned with RED?
Yeah, it's just basically Moses.
Okay.
Okay, so the current existing models are basically built for languages like Arabic, whereas the ITG-style grammar that I'm using doesn't have any of that monotone bias, which turns out to be quite a good thing for Chinese, which isn't very monotone. But in the Arabic case, we're losing power by doing that. So really, the grammar is just not the right one for Arabic. So we need to, if we want to do better on these sort of languages, we need to have some way of encoding those biases in the model, or having the model able to learn them rather than encoding them.
Why can't the model already learn them? You have a distribution over the 3 types of rule. Why can't it learn that the swap rules are unlikely?
Because the problem with the ITG model is it doesn't condition on the size of the variables you're reordering. So you can't learn that, so Arabic doesn't have no reordering, but it just has little bits of local reordering. But you can't learn to differentiate between local and global reordering in an ITG. So if you increase the probability of reordering, then you expose yourself to the problem of taking the end of the sentence and putting it at the start. And the only thing that sort of conditions that is what the language model thinks. And so there's lots of cases where the language model will tell you that, yes, you should move this determiner to the other end of the sentence. And that's a bad idea in translation. Whereas the phrase-based system has the linear distortion penalty, which for something like Arabic is far more effective.
Good, thanks. That was clear. I mean, there's sort of a natural question, which is, are you sure you really want to use? Are you sure you really want to use ITG? Could you turn the system into something that uses lexicalized
Yeah,
rules?
I'm definite that ITG is not the answer to the translation problem, but it's the reason I'm using it here is it's nice and simple for the experiments.
I mean, I guess I'm asking, is your next step to use something that's lexicalized and to use it during decoding as well?
I'll talk about that in a few slides at the end, and we'll sort of discuss where to go from here. So there's an analysis of why the Bayesian model may not do very well compared to the baseline. But then we also have the effect that the initialization does really well. And so what's going on here, if we look at the alignment, we know from past experiments that real translations with manually annotated alignments do factorize to binary factorizations in about 98% of cases. If we look at automatically generated alignments, they factorize in about 20% of cases because they're far more noisy. So what we're doing in the initialization by making things factorize by deleting alignments is basically cleaning up the alignments to make them factorize, and that turns out to be quite a good idea, and it's effective. So we now have another effective heuristic for MT. But so the thing is to learn how to do that with a probabilistic model. So if we look at the alignment, so here on the left is a heuristic alignment standardly used in phrase-based translation system. On the right is a single sample out of the Gibbs sampler. So I emphasize that I'm not actually learning alignment, we're learning a distribution, but this is just an alignment from a single sample. And the brackets on the edge of the alignment denote the actual internal structure to try and give you a sense of that. And we can see this effect that the alignment is just cleaner on the SCFG based model because it doesn't allow outliers like that of and has a bias to more locally coherent phrasal units. So we don't see things like this, which you see a lot in the current heuristic models, which are just extremely implausible alignments. So discussion on this work. So the Gibbs sampler is effective for scaling the inference. It really works quite well. There is this heavy reliance on the initialization. We'd really like to be able to initialize the model randomly and have it perform well, but it doesn't. There's a lot of local optima. It really needs to be initialized with a good alignment. And this also points to that the particular operators are not the best ones. We need ones which give better mobility in the sampler. And we need to be able to make bigger steps in sampling in order to get around some of these local optima. As I've said a number of times, the ITG grammar is not a good one for translation, and so a main concern is finding better grammars. It's relatively straightforward to imagine extending these sort of ideas to sampling tree substitution grammars. and also sampling grammars in the style of high-row. The main concern with something like high-row is coming up with a good prior distribution over high-row rules, which is actually non-trivial if you think about it for a while. But, and finally, sampling the constituents as well, which is very straightforward to do with the way I've described the model. The only concern there is that the complexity would be quadratic. So for every split we might be able to do, we need to sample over the space of possible labellings for the two children. This is better than cubic in the variational inference, but we really want it to be linear to be able to scale to large amounts of data. So to summarise, so what I've done here is I've described the model, a model that we can use to induce grammars, and shown ways that we can use the Bayesian priors to create models which encode our preference for how this translation process operates, and so that the model can be biased towards learning small, compact grammars. I've shown a couple of ways of doing the inference and discussed the various trade-offs between the variational inference, which gives us very nice dynamic programming algorithms, but then makes us use such things as truncation that loses the real ability to explore interesting grammars. And we've shown that we can scale this to real amounts of data. So if you look at the prior work on these sort of inducing these sort of grammars, there was always a heavy restriction on the length of the sentences, generally down to about 20 words. Here we're doing inference with sentences, in this case up to 80 words, and on millions of words. And so main concerns for the future are exploring more plausible grammars and increasing the mobility of the sampler so that we can have less reliance on the initialization and less concern about encountering local optima. Thank you.
So, do you imply that the variational operation is not scalable enough?
Doesn't scale.
So when you talk about scalability, you use if something, right? Do you imply that the variational operation is not scalable?
Yeah, so this runs contrary to a lot of the literature in Bayesian inference. Generally, variational inference is used as a way of scaling models. The problem here is the restrictions that we have to make to do the variational inference, because the thing we really want out of the non-parametric model is the ability to do inference over the entire space of possible phrases, because we don't know which ones are good phrase translations. And that doesn't work well with dynamic programs and variational inference. So the variational inference is very good when you have a set space that you're exploring. So if you know the grammar beforehand and you just want to learn the weights, or you can restrict it quite heavily. And that's the way it's applied in most Bayesian models. But in our case, we really want to be able to explore the space in a somewhat unrestricted fashion. So it's interesting to think we don't have to do variational inference or sampling, we can combine the two. So, and that's probably where some quite effective algorithms might lie in terms of you can sample subsets of the space and then perform variational inference and iterate in that way. So there's no restriction on combining these sort of things.
Yeah, I mean, it's probably worth saying that if you had a finite grammar, at least, a more obvious way to do sampling would be you construct the parse forest using inside-outside and then pull a tree out of it all at once, rather than taking a walk. But of course, as you say, that might require n to the sixth time.
Yeah, so even...
and worse if you've got non-terminals.
Yeah, and if you wanted to do something like a tree substitution grammar.
Yeah, so this is kind of a cute alternative, and I wonder if people should be using it for doing other kinds of parsing.
Yeah, so there's obvious ideas you could try in dependency parsing and other areas where, you can have things like long-range features for a start, but also just more complicated prior distributions.
Yeah, I mean, dependency parsing is a good example because you don't have the non-terminals. You may have some restrictions, like you could introduce them later. You have to go through a valley to climb back up. You'll be reluctant to reattach something. To attach a subject to somebody who already has one or something. But,
and those sort of problems are still faced by this sampler, and that's why I talk about the mobility and really being able to take larger steps. Because as you say, some decisions mean making two implausible decisions to get to a plausible one, and so you need to be able to make bigger decisions to get around this.
Larger never meant.
Yeah.
Okay. Have you thought at all about how you would extend your tree sampler to the case where you have multiple non-terminals?
So you mean in the sense of a flat FCFG, but with more than two, or?
Well, suppose you have an ITG with more than one non-terminal.
Oh, you just mean the set of non-terminals. Well, that's what I referred to as being relatively simple to do with a quadratic sampler. So every time you split a node, say a phrasal translation, just sampling over rather than just all the splits, but all the splits with all their labels, which.
I guess that's reasonable. I mean, I'm a little worried.
Well, that's quadratic, so it's not ideal.
Yeah, I'm worried, that's not the part I was worried about. I was worried about the mixing time.
Well, so my actual feeling is that will improve the mixing. So the problem we face currently with only a single non-terminal is when you're sampling the internal structure of the derivation, there's very little information because whether you have 2 children or 3, or whether you have left branching or right branching, there's no real difference if you only have a single non-terminal. And also in terms of so having more non-terminals the probability distribution will be more varied, and that will direct the model.
Actually, it's not the mixing time I'm worried about, it's the rejection rate. So I'm worried that maybe all of the ways that you might split will end up being bad because you need some rule that works here, and also you need a choice of non-terminals that works with the thing below. And
so the obvious thing to do with non-terminals is to introduce a sampler just for the constituent. So you imagine you have a derivation, and then you can run through quite easily fixing the tree structure and just resampling the labels in a fashion. So rather than sampling them at the same time, just have another operator that runs through it. So
right. Okay. So kind of a let's say an upward-downward algorithm.
Yeah.
It fixes the structure of the tree.
Yeah. And the whole problem is when the tree varies. If you fix the structure of the tree, you can start making much bigger leaps. Yeah.
I'm still curious. You talked a little about your distributed training. What was the runtime for a single processor?
I think that was about a day. It was about a day to do the 1500. Sorry, say that again?
How much improvement did you get?
Oh, sorry. When it was distributed, it was about a day. And so it's pretty much linear, I would argue. That the communication time is relatively low. So if you imagine the single processor would take 8 times as long, so maybe 8 days.
Never did the single processor.
Well, only in that example I gave for the posterior, and that was up to about 250 samples. So if you imagine that's a... yep.
Is that the Nehalem or the Fenrir processor? Do they have 2 caches, share cache?
I couldn't actually tell you.
Which is the what computer is it?
It's a particular...
okay, so probably most likely then they have separate caches. They don't share the cache.
It's Nehalem, which is the newer one, isn't it? Yeah, it's that one. So these are relatively new machines.
Unless somebody else has a question that they haven't asked. So nobody else
So at the beginning, you said you want to remove all the heuristic in the current machine transmission pipeline, but then in the end, in all experiments, you use all kinds of heuristic, like for the initialization, for the decoding. Do you think this really, this Bayesian approach really be able to remove all the heuristic we had?
So we're a very long way from removing all the heuristics, and that's why I talk about the initialization being a problem, because obviously you don't want to be running an alignment model to initialize this. So yeah, this is still very much early work. I'm not claiming that this is a finished approach that you would use. It's very much a proof of concept that we can actually do this. We can do principal Bayesian inference on a large scale. So the question then becomes, well, what should we be modeling? What grammar should we use? And how can we improve the sampler to get rid of the initializations? Yeah, so there's many things still to be explored. But I agree wholeheartedly that there's still many heuristics there that I'd like to see removed.